Learn physics with J Science.
Hello guys, welcome to another video. We're going to solve quite a number of questions in this particular video, and those questions will be on changes in state of matter, and also particle model, which is contained in the AQA GCSE paper. For question 1 says, two students investigated the change of state of steric acid from liquid to solid. They measured how the temperature of steric acid changed over 5 minutes as it changed from liquid to solid. Figure 1 shows the different apparatus the two students used. You have student A's apparatus, you have student B's apparatus. Then says, choose two advantages of using student A's apparatus over that of B. One of the things we noticed here is that for students A's measurement definitely will have a higher resolution, and also for student B, he or she will likely misread the temperature because of some of the errors that might arise from that thermometer. Moving on, it says student B removed the thermometer from the liquid each time he took a temperature reading. What type of error would this cause? Definitely that's a random error by the way. And then student A's result are shown in figure 2. I have figure 2 right here. Let me just make it smaller so you can see the whole thing. So you have 64 minus 55.6. Alright, that should give you 8.4. Alright. Use figure 2 to determine the time taken for the steric acid to change from a liquid to a solid. That's from the time it, let's check the question again. What's it saying? The time to change from a liquid to a solid, that's from 160 right here. Let's look what we've got here. Let's just like it's 740 seconds. E says calculate the energy transferred to the surroundings at 0.40 kg steric acid changed state from liquid to solid. The specific latent heat of fusion of steric acid is 199,000 joules per kilogram. Use the correct equation from the physics equations sheet. We don't have that right now, but I'm gonna write that equation on the screen for y'all. We'll have the mass. Alright. We have the latent heat, a specific latent heat, that's F, and then we're asked to calculate the energy transferred. So the equation for that is energy transferred equals to mass times latent heat, in this case of fusion, substrate F, and that's 0.40 kg times 19930 joules per kilograms. This should give you 79,600 joules. After 120, that's 1,200 seconds, the temperature of the steric acid continued to decrease. Explain why. The acid is losing its temperature to the surroundings. So it's at a higher temperature than the room temperature, so it's gonna come down, lose its energy. So let's just put that down in words. We can say steric acid. Let's start again. Steric acid has a higher temperature than the surroundings. Alright. Let's move on to number 2. The figure below shows a balloon filled with helium gas. Describe the movement of the particles of helium gas inside the balloon. Now, one of the main things we can see here for the movement of the particles, as the case may be, so you can see that the particles have range of speeds. So they're not moving at constant speed, like all of them the same speed. It varies. But the moving, that's the major thing. They're always moving. And the second main thing you can talk about here, as you can see, it's a 2-mark question, so you expect to talk about 2 valid things here. The particles have range of speed, um, and they also move in different directions. We're talking about random motion there, colliding. Let me do that again. Colliding with themselves and with the wall and what of the container. Yeah, that's about that. What name is given to the kinetic energy and potential energy for the particles of helium gas in the balloon? That's internal energy. Write on equation with links density, mass, and volume. Simply put, that's density equals mass over volume. That's a popular one right there. This is the helium in the balloon has a mass of 0.0254 kg. The balloon has a volume of 0.0141 meters cubed. Calculate the density of helium. Choose the correct unit from the box. Number one, when it comes to density, the unit is always kilograms meters per meter squared. I mean cubed. So kilograms meter cubed. And right here, you have the equation density equals mass over volume. That is 0.00254 kg multiplied by, is that multiplication? No. Okay, let's bring this down. Let's bring it down. I think it's much better now. 0.00254 divided by the volume, which is 0.0141 meters cubed. And if you plug this into your calculator, you should get 0.18. All right. Moving on. Let's see what we have for lesson 3. A student wants to calculate the density of the two objects shown in the figure. Describe the methods that the student should use to calculate the densities of the two objects. All right. Now, when it comes to the description here, we should start with the the general thing. All right, and then we'll pick each one, like one after the other. All right, now here we can say that for both okay, we can say for both objects, that's the metal cube and the statue, small statue right there. All you do is to measure mass using a balance, and then go ahead to calculate density using density equals mass over volume. That's on the general term. And then if you're to pick this one after the other, you have the metal cube. How do you go about this? All you do is to measure length of cube of the cube's sides using a ruler, and then you calculate the volume. So since you have the mass on ground for the metal cube, you calculate the volume and plug that into this equation, you get the density. And then for the small statue, that calculating the volume is quite different. We have the masses now. Now all you do is to immerse in water and then measure the measure the volume of water displaced in a graduated cylinder. You have to do this in a graduated cylinder. That gives you an idea of how much displacement do you have when it comes to the water. So in this case, the volume let's put it this way: the volume of water displaced equals the volume of that small statue. And all you do from here is that you would plug it into that equation right there. Question 4. A student investigated the cooling effect of evaporation. She used the equipment data logger and probe shown in Fig 1 to measure how the temperature of a liquid changed as the liquid evaporated. So you have the data logger, you have temperature probe, and all of those things. Which type of variable was the temperature in this investigation? Let's just make this smaller in this case now. Now let's define what these three guys are. You have the control variable, which is what you keep constant. You have the dependent variable, which is what you measure. You have the independent variable, which is what you change throughout the experiment. So for this particular experiment now, what you're actually measuring is the temperature, which is the dependent variable. So we keep that a tick. Then it says before the investigation started, the student checked the accuracy of 3 different temperature probes. The student put the probes in a beaker of boiling water that had a temperature of 100 degrees C. The readings from the 3 temperature probes are shown in figure 2. Where is figure 2? Is this figure 2? No. I think figure 2 is down here. Yeah. The readings from the 3 temperature probes are shown in figure 2. Probe A, probe B, probe C. Then it says that, let's see the instruction right, which of one of the probes was the least accurate. Write the correct answer in the box and then give a reason for your answer. Alright. The reading is 100 degrees. That's the actual reading. And the least accurate would be the one that has the greatest difference between the actual reading and the, what you got from the probes. So 99.8 is not too far. Let's just have about 0.2 difference. So it's kind of close, but not perfect. 100.1 for probe B, very, very close. Accurate as well. To off, and then 103.2 is way off the mark. So this we'll go with probe C, which is 103.2, and the reason is that the difference, what we choose and see, the difference between the reading and the actual temperature is largest, or is the largest, as the case may be here. Let's move on to C. C says figure 3 shows how the temperature recorded changed during the investigation. Let's see what this is saying. You have the temperature on the y-axis and the time on the x-axis. You use figure 3 to determine the lowest temperature recorded as the liquid evaporated. Yeah, the lowest temperature recorded here is actually somewhere around here. Yep. And then when you trace this, let's trace. Yeah, this gives you somewhere around 12 degrees C, and then you might get maybe around, let's just say between 12.0 and 12.22. Just to give there might be little differences between students' answers there. 2. Figure 3. Use figure 3 to determine how long it took for all the liquid to evaporate. Give a reason for your answer. Alright, how long? That's around 140 if we're working with the first dot. That's around 140 seconds. This is it. 140 seconds. And give the reason. If you check this graph now, after 140, the graph begins to rise. So that's kind of explanatory. When I said the graph begins to rise, the temperature is on the y-axis. So if it's rising, the graph is rising, then that means the temperature is rising as well. So you can see after this point, the graph begins to rise. That should be S, not Z. How would increasing the starting temperature of the liquid above 20 degrees C affect the rate of evaporation of the liquid? All right. What that would do is that would definitely increase. There will be an increase in the rate of evaporation.